Today for our Quantum Wednesday, we have speaker Leonardo Banchi, who's going to talk to us about efficient tensor network simulations of weakly measured quantum circuits. So I know I'm particularly excited to hear about this one. And you can go ahead and take it away when you are ready, Leonardo.
Hi, hello everyone. Can you hear me properly or?
Yeah, you're great.
Okay, great, thank you. So let me share my slides. Now it should be fine.
Oh, and I'll just ask one more question before you get started, Leonardo. Do you prefer people wait until the end for questions, or are you cool with people kind of jumping in?
You can always jump in and ask questions, or feel free to make them at the end. But I prefer questions, iterative questions. So whenever you have something to ask, please do.
Okay, great. And I
Um,
will keep an eye on the chat and try and jump in if there are any
yeah,
that.
I won't check the chat. So, just speak. All right. So, hello everyone. I'm Leonardo Banchi. I'm a professor at the University of Florence, and I'm mostly interested in at the intersection between many-body physics, quantum computing, and well, machine learning. And today I will speak about this recent paper that we did with Darren Pereira, who's a PhD student at Cornell. And the topic is about efficient tensor network simulations of weakly measured quantum circuits. So, how can I move this thing? I mean, if you have seen the link in the archive, you have already seen this. So let me tell you also what are the main ingredients. So here in yellow, just a summary. So we present a tensor network-based method for simulating weakly measured quantum circuits. And here, the main idea is to use a Markov chain to efficiently sample the measurements. So in green here, I'm putting some of the applications. So the applications of this method are for validating quantum computers, of course, those capable of mid-circuit measurements. And I have in mind in particular these ion trap quantum computers. But I mean, the framework here is general and not related to a particular setup. And another application, which is perhaps my personal main interest, is in generative machine learning applications. So ideally, something reasonably complex for this setup. And another application, which is more for people interested in condensed matter physics, is for measurement-induced phase transitions. So currently, just to give you some numbers before entering into the bulk of the paper, so basically we are able to simulate even hundreds, like 500 qubits for circuits that exhibit area law. Of course, those are the ones that are efficiently simulatable using tensor network methods. And for all the details, you can check the archive paper. Okay, so then let me start with the bulk of the paper, and let me make a detour first, because I want to also to explain my personal motivation behind this study. And so my personal motivation is to start investigating using quantum tricks, temporal stochastic processes. So temporal stochastic processes, of course, are everywhere. So one example here that I'm taking is a stock market. So, and ideally, we would like to model processes like this, but using a quantum simulator. So first of all, how do we model processes like this? And so one example, so if you are coming from a theoretical physics background, and especially like quantum field theory, so perhaps you have heard the name of Chern-Simons theory, and you might have seen that the Simons Foundation, which was funded by this guy, now currently sponsors a lot of research in the world. And you might have heard the story behind the Simons Foundation. So this guy, the one also behind the Chern-Simons theory, started a firm that basically were using a model for describing the stock market, which, I mean, initially at least was based on a Welsh algorithm, which is again based on hidden Markov models. So hidden Markov models are quite successful, and apparently you can also make some money using them. So how do they work? So for instance, here I was focusing on this particular example where you have the euro versus Singaporean dollar price. And so these things work basically observing some data. So you have some observed data. So here, for instance, the stock price today. And you also have some other data which might be correlated with what you're interested in, like some rest of the market. So something you observe. But then you also have some other hidden degrees of freedom that you can't observe because, of course, you cannot see everything. And so what you do, so you have also what you have today, and then you want to use this knowledge in order to make predictions, like also to make what is the next, what's going to happen tomorrow to this stock price of the euro versus Singaporean dollar. In principle, you could also make prediction with the rest of the observed market, but you really don't care, and you want to add this complication to the model. And then, of course, there is also everything else, which is the things that you don't observe. So mathematically, what you do is that basically you compress everything into something which is observed and something which is hidden. And the idea here is that everything that is correlated with your data is somehow written in this kind of hidden variables, which are relevant to predict the future observations. And so the main idea is here like in tensor networks, so where in principle, with a suitably large bond dimension, you can model all the correlations in a complicated quantum state. But what you do here is that you replace with the huge hidden states with a finite memory. And you train the models in such a way to contain all the relevant information that you need to predict the future. So now, how does this work? So basically, you work with hidden Markov models. So you have observations, and then you have a memory. So this is nothing but a stochastic model. So everything is kind of described by a stochastic matrix, which takes which has three indices. So x here is the observed value at a particular time. Then alpha and beta are the memory states. So beta is the memory state before the observation, and then alpha is the memory state after the model emits a value and then updates also the memory. So if in a learning setting, what you have to do, you have to learn this transition matrix. And one possibility in order to do this efficiently is to write like a maximum likelihood, which is, I mean, something like this, where you have the probability. Well, basically, you want to maximize the probability of having the particular data string. And so this can be expressed as a kind of matrix product. And then you can also train this model efficiently using, for instance, the Baum-Welsh algorithm. Now, why this is important? So this is important because now it's quite clear, and there has been at least two independent studies that I'm aware of. Namely that if you now replace the classical model using classical transition matrices with a quantum model, where instead of having transition matrices, you basically have cross operators, then somehow the resulting model is more expressive, which means that it requires less memory in order to basically reproduce the same statistics. So let's try to understand this a little bit more, which kind of motivates my interest in quantum stochastic simulators of classical stochastic processes. So the idea of quantum simulators is that basically you replace the same structure, but where somehow instead of observed and hidden states, you have the physical indices, which correspond, for instance, to the, I don't know, your physical degrees of freedom, like spins in a spin model or qubits in a qubit model. And then you replace the hidden states, so the hidden memory with, the bond dimension. And so now you can also think of this as a kind of matrix product state, but in time rather than in space. And so here in this language, what you do is that you replace the transition matrices with K, which are now basically Krauss operators associated to some measurement. And so the probability, so the big difference here is that the probability of getting some outcome X here can be written as this. So as the absolute value square of some probability amplitude, which is given by the evolution of the quantum state.
Yeah, I have a quick question on this
Oh.
slide. So I understand in like this one. In the previous thing, in the classical setting, I understand the two wires, what those correspond to, but here, what physical and bond, I don't know what those mean.
So here the wires. So here still is. I'll be more precise later. So here, what you do here is that you the physical it corresponds to the observed value, and the bond dimension is some hidden state. So you can think of this as in a quantum computing language. You can think of this as the physical as some qubits, those that you measure, and the bond, which is like more in the language of tensor network, that could be some other qubits that you use as a memory. So K can here be like a unitary that basically couples the let's say physical or the observed qubits with the unobserved qubits. Then you measure the observed qubits and you use the others as a memory. Okay. So basically, you can replace this operation unitary plus measurement as a Krauss operator.
And you know what the Krauss operators are, or no?
Well, that depends. It depends. You may want to learn them, or you may want, or
right.
you can construct them if you have some, I don't know, toy problems in mind.
Okay.
Yeah.
Okay. Yeah, I think makes sense.
All right. Thank you. Okay, so now you have this two ways of generating probabilities. So one where you have this kind of tensor network or quantum circuit, depends on what you're more familiar with. And so you keep, so these are in principle two very different models. So it's also quite difficult to make a fair comparison since we have, different models. But and so people have studied different ways, generalizations, let's say, to this simple idea, where you can build the model using matrix product states on a general field, so not just complex numbers, but also real numbers or whatever. And then you can also make what they call like a Born machine. So the Born machine is basically what I presented here before. So you have you want at the end to take so you're working with amplitudes rather than probabilities. So at the end you have to take the absolute value square of the amplitude. And in this language, this absolute value square basically corresponds to this up and down circuits. And then you can also make things more general. So you can also work with density matrices rather than pure states. And in the only difference using density matrices is that you have some other other basically index that is contracted, and you have this structure over here. So you can play with this structure in order to have complicated models. And in this paper by Glasser and others, basically it's written in a kind of complicated mathematical way, but what they have shown here is that so there exists some problems for which I mean the quantum simulators have a lower complexity. Okay, just to compress what's written in this slide. So, so that's basically it for this paper. Then there is another version of this, which basically kind of describes what are the models for which we can expect a provable quantum advantage. And those are the models which are called unifiliar, or also epsilon machine. That's another name for this model. Where in the classical version, they have this structure that you can see over here. So where the Tx alpha beta, which is the classical transition matrix, can be written as an emission matrix that, given the memory beta, emits some observation x. And then the big difference is that here you have like a discrete way of updating the memory. Namely, and this discrete update is a function of the emitted signal, which is a stochastic variable, and beta, which is the previous memory state that at this stage is kind of analytical. And so here there is a direct mapping between the true quantum simulators and which has been studied in the literature. And what they have shown using this language over here is that so the resulting models asymptotically can also use much less memory compared to the classical stochastic process, which means that somehow on average, so if you study the average memory that you need to store in order to make future predictions, this can also be can also have very different scalings for the quantum model and the classical model. So here now we have basically two questions. So we know from previous literature that these quantum simulators are more expressive than the classical hidden Markov models. And the way to write this more expressive, at least in a mathematical language, is that there exists some stochastic process such that somehow the quantum model wins. And processes, for instance, that admits this exact mathematical structure, which is called epsilon machine, so a rigorous advantage. But the question is that, so real-world models normally cannot be exactly expressed as an epsilon machine, and so we can expect imperfect simulation. And so also one of the questions that I had is whether this advantage persists. And so also another motivation is for generative machine learning. And so my personal interest was also to find quantum machine learning models that generalize with less data. So what we have shown in this, well, starting from 2001, using this kind of formal techniques to study quantum machine learning, is that the generalization error, which is basically the difference between the training error and the testing error, so this is kind of linked to how much the classical data can be compressed in a quantum state. So the idea here is that the more complexity you put in the quantum model, so the lower is the training error, which is kind of this red curve over here. But then somehow, like in classical models, there is a certain transition after which the model starts to overfit. And the difference between the testing error and the training error is basically linked to how much these data are compressible using quantum representations.
I'm just going to jump in right here. We've got one question from the chat.
Sure.
Amir, do you want to ask your question?
Thank you so
yeah.
much. So I have a question a few slides back where you were showing the MPS part.
This one or?
A few more back. Yeah,
This?
this one. So you mentioned the physical and bond. In this case is physical x1 and xn and bond sigma 1 and sigma n minus 1.
Alpha 1, alpha n are the bonds, yes.
Yeah. And quick question. In the final one, how is that equal? Because like it has x1 to xn as the free indices, but in the equivalency one you have two sets of x1, xn. Feels more like an MPO than an MPS.
Yeah, so the one is an MPO. They are not equivalent, they are different models. And so for instance, in this table here, they were studying, let's say, whether one model can be mapped to another, and
Mm-hmm.
so that's somehow the meaning of this table over here. They are not equivalent; they are different models. So, for instance, this one, so the first one, so when this F field is the real number, so that's basically the classical hidden Markov model. The Bohr
Mm-hmm.
machine is the pure is a quantum model using pure states, and the locally purified is basically a quantum model using mixed states as a kind of resource, like an MPO, as you said.
So what does that like the equal
Is
sign mean? If I can ask my
it
question.
actually sorry
What does the equal sign
sorry
mean
I mean.
then?
Oh, no. The equal, so these are different models. So the first T, and so T here is something else. So so the is I mean, I took this slide from that paper, to be honest. So maybe
Mm-hmm.
you are puzzled because it's the
Yeah.
same T, I guess.
No, the third one, I'm wondering why. So forget about the first two. I'm thinking about the third one. Is the left side equal to the right side?
The left
Is the
side.
left hand? Yeah. So the
I
dense
think it's a
tensor T.
definition. It's a definition. So you create a model in this way. The left
Mhm.
side, yeah, exactly.
But then how does that work? Because the left one has like a dense tensor T with n free indices, where
Uh-huh.
X was the physical, but then the right one has double the free indices, which is the part that's a bit
No,
confusing.
because they are forced to be the same. It's like when you are taking a measurement of so if you have a density matrix and you want to extract a
Mm-hmm.
probability distribution, you take a particular diagonal matrix element. So here is like you want to have a diagonal element of a tensor network. So the top and bottom, they are the same index.
Wait, so
Is it?
you're like contracting the top and bottom as well?
No, you for instance, so you assume that this is a tensor with the two n indices, and you
Mm-hmm.
evaluate this tensor only for the indices where the top one and the corresponding bottom one are the same.
I see. Okay, okay. Makes sense.
Yeah. All right.
Yes.
Um, Other questions?
Um, for the moment, it slipped my mind. If I remember it again, I'll ask it.
All right.
Thank
Um,
you.
Thank you. Then I can move on. So my personal motivation, as I said, was to see whether we can exploit this memory disadvantage in compression in order to in order to see whether there are some models, quantum model, sorry, sorry, whether there are some data for which a quantum model can provide an advantage uh, for uh, for generalization, namely that can learn the process with less data. And so that's something that I started to study in this paper, which is accuracy versus memory advantage in the quantum simulation of stochastic processes, which is kind of also one of the motivation also behind the more recent study. So here the idea is somehow explained in this diagram. So if you assume that somehow you have models with satisfy this exact mathematical structure, which is called epsilon machine, then you can also model, you can also translate exactly using some theory the same model in a quantum model. And this is rigorous. So it has the same perfect accuracy. And so this is also the memory size. The vertical axis is the memory size. So the quantum model is somehow is known to have also less memory. But somehow real data don't have this classical epsilon machine structure. So the main assumption behind that paper is that, so first we map the real data into a classical epsilon machine in principle. So here we can also map this perfectly in a quantum simulator. And then we go back and compress the model in order to get the same imperfect accuracy. And the question is whether we still get an advantage. Okay, so this is like kind of a way to study whether somehow this quantum advantage persists. But in applications, so this long path is not what you want to do. So in applications, what you want to do is that you want to find a direct mapping between the real world problem and the quantum version of the real world problem, although somehow theoretically this is not known and must be somehow optimized numerically. And also in this paper, something that I did was, although this is the main somehow motivation, I was also studying directly models that can be expressed as an epsilon machine and investigated the disadvantage when we compress them to what would be the real world use case. And so basically, I mean, what I have shown also here, I will be quite quick because this is again something slightly different. Is that yes? So this advantage also persists when you compress and you lose this epsilon machine structure. Now, and now here things are starting a bit more interesting for applications. So how do you optimize the quantum model efficiently, considering that the probability, so whenever, especially when you have long time series, so the likelihood is gonna be very small, because these are probabilities that are exponentially small in the number of observations or in time, if you want. And so clearly it's very easy to go below the machine precision in computer simulations, even classical computer simulations. And so you really want to avoid having to deal with these exponentially small probabilities. So here, one trick that I studied in the same paper is that you can define some normalized forward and backward states. So where the forward states and backward states are kind of generated here in the right. So whenever you have these cross operators, if you are familiar with tensor networks, but these cross operators are nothing but unitaries and followed by some measurement in the language of quantum circuits. And so what you can do here is that you can take the gradient of the log likelihood and with respect of this tensor network elements or cross operators. And this gradient can be expressed using this forward and backward tensors. And since these are normalized iteratively, so here the complicated exponentially small probabilities do not appear. Okay, so you are not studying directly the probabilities because, for instance, this pk is exponentially small, but the logarithm makes that a reasonable number. So you're taking the gradient of that in such a way that you never have to deal with exponentially small probabilities. So here, all these gradients are, let's say, large, and so the model is kind of trainable. And also, not only you can also estimate the gradient, so by keeping a history of the normalization factors, you can also compute directly the log likelihood, again, avoiding these exponentially small probabilities. And also, once this gradient is computed, you can also optimize directly the cross operators in such a way that they keep defining cross operators. So with the sum over k is basically so k dagger is the identity. Using basically tricks by Riemann optimization, and in particular using, you can show that this can be mapped into an optimization of what is called a Stiefel manifold. And there are explicit solutions to the somehow the gradient update in this manifold. And so if you use this, you never go out from the space of cross operators. And so, I mean, what I found empirically is that this works pretty well in simulations. And then I was using some, let's say, very simple data. And what I have shown here is that, so if here I was considering like a very simple model, like a stochastic clock. A stochastic clock is a model where somehow you reset the clock with some probability. And so you were studying somehow the distribution between how many times the clock ticks before the reset. And so I was studying a very simple model where the exact model was this in black. And then somehow using the same number of data, you can see that the quantum model were able to fit the data much better. And so here somehow you have a very, I have to say, preliminary and numerical evidence that somehow these quantum models can also learn with less data. And I mean, I was also studying with some real world, but yet very simple data like lithography, which again, some moderate advantage can be observed. And okay, so this is just to show how the training looks like. So initially you have, so the gradient is very noisy, but then after sometimes somehow you have like a kind of a transition, and the model starts to train and feed the data very well. Okay, so this is just a conclusion for this first part. So we know that somehow we can get quantum advantage in the simulation of classical stochastic processes, and this advantage persists even when we relax this assumption of exact simulation, which is somehow what we can understand from what we can expect from the real-world data. And so these quantum simulators can display higher accuracy for a given memory, or that alternative, so they can achieve the same accuracy by retaining less information from the training sequence. And so again, some interesting prospects for me here, at least, to study generalization. So to make this connection between compression and learning more formal. And also to go to quantum tensor networks with a large bond dimension, and then also to make the training algorithm more efficient. So because if you're dealing with tensor networks, then this training technique is quite handy. But if you want to use, for instance, a quantum computer, where in place of cross operators you have unitaries and measurements, then somehow also this must be optimized and made better. Okay, so now enough for this introductory part. So let me now go to this new paper, which is about the tensor network simulation of weakly measured quantum circuits. So my main motivation is this. Okay, so now you have shown that something like this is interesting. So there is also a reason to map models, so to transform models like this into a quantum language. But if you want to now deal with let's say not zero-dimensional data but one-dimensional data in time, then we need to extend this to something more complicated, which is something like this. So now you don't have only time, so we have both time and space. And so here again, each line could mean like that we are in a quantum computer. So this blue spot means some unitary. And so we do some unitary operation in time, and then we measure some of these qubits in order to extract our observations and model our physical data. And then we keep doing this operation multiple times and keep measuring. Okay. So basically, so we are currently studying this process, but we realized that in order to study this process, we also need a convenient numerical method in order to extract these numbers. And so here, in particular, we want to simulate the measurement outcomes, which is actually what we want, because we want to simulate this kind of stochastic processes. So how do we? So we studied this as a model, and this model now is inspired by what is possible nowadays using this quantum computers capable of mid-circuit measurements. And we also wanted to study the model, which is kind of complicated enough in order to somehow test our technique. And so the model that we did consider is something like this. I apologize that now space and time are swapped. So here now space is a horizontal, time is vertical. So Q1, Q2, Q3, Q4 up to Q6. So those are physical qubits that are separated in space. And so time goes from bottom to top. And so in our model, we alternate basically layers of complex unitary evolutions between pairs of qubits. So if we keep repeating this structure and we don't measure the circuit, so what's going to happen here is that somehow this creates a large amount of entanglement, so volume law entanglement. And so here, tensor network methods normally don't, they're not accurate anymore because the bond dimension becomes very large. But then now we add a competition. And the competition here is that we add some measurement, weak measurements that destroy this entanglement. So we have a competition between a unitary circuit that creates a lot of entanglement and a measurement which kind of destroys the entanglement. But it's a weak measurement. So being a weak measurement, it doesn't completely destroy the entanglement, and we can also play with the strength of this measurement in order to see whether somehow we jump from a regime where our tensor network simulation is efficient to a regime where we have volume law entanglement, where clearly it won't be efficient anymore. And so now the algorithm in the paper is written like this. So how do we simulate the outcomes of this measurement? So here so I want to say that somehow models like this are studied a lot in condensed matter theory in order to study measurement-induced phase transitions. Normally, at least to the best of my understanding of the literature, is that people in that literature, they are not really interested in the measurement outcomes, while we do. Okay, so we do because the measurement outcomes is exactly what we want, because we want to reproduce what you can observe. And so here, what we wanted to do is to have an algorithm which is in order to be able to sample these measurements in an efficient way. And so this is the diagram from the paper, but for this talk, let me also jump back to some of my old sketches, simply because I have more of them and so I can present this in more details. So first of all, can you see my mouse over here? Because now the mouse is going to be quite important to... Yeah, all right, great. So suppose that now we have a structure like this. So we are starting from a matrix product state at time t1. So this is the state that you get after the application of your quantum circuit. And then now we are adding this kind of red extra index. So this red extra index is the weak measurement. So we keep repeating this. So we have an extra index which models the weak measurement. And then we keep repeating this structure with another extra index. So how does this work? So how do we map this in this language? So you can see this thing at the bottom. So we have our matrix product state. And then what we do is that, so where the vertical indices are the physical indices. So what we do here is that now we perform a weak measurement. And in order to perform a weak measurement, we do something like this. So we couple weakly our system with some measurement qubit. And then once we couple quickly this to the measurement qubit, we do a projective measurement on these ancillary qubits. So that's exactly the idea here. So we have our MPS. We do this kind of red thing that couples my physical qubit to an extra qubit, which is initialized in 0. And then we do a projective measurement on the physical qubit. Now, this whole thing here, it has an index, which is the one here that is measured. And this extra index here is this kind of extra red thing on this stuff. So the one on the top means that we basically repeat this kind of structure multiple times, now alternating this kind of measurement layer with some extra entangling layer like this. So that's somehow the main idea in order how do we build and propagate our tensor network. And so indeed, so we keep applying this kind of, so we start from some physical qubits. We keep applying this kind of brick wall structure in order to create a lot of entanglement. And then we apply these things in order to do some, to simulate the weak measurements. And so once we kind of contract all the indices here, we end up with a tensor network like this, where we have, per site, we have 2 indices. So one, which is the ancillary index that we eventually measure, and the other one, which is the physical index that basically keeps propagating. So once we have this, then we plug these physical indices back and we repeat this structure over here. So then how do we model and how do we estimate these observed outcomes? So here, everything would be like a pure state without the measurement. So in order to simulate the measurement, we make a Born rule. So we take the bra, we take the complex conjugates, which makes a cat. And now we don't care about the qubits that we don't observe. And so this means that we have to contract the indices of the qubits that we don't observe. And this means that we have now this extra structure over here, where this means that we are contracting over the indices that we don't observe. And here we have to take a measurement of the x1, x2, and x3. Again, here we have, as in the previous question, so we have several indices, but so here we force this x1 and this other index in the bottom to be the same because we are basically estimating diagonal elements of the density matrix. Right. Now, how do we sample efficiently from this? So first of all, we can move this extra index to some vertical index, which is what I have done here. And so before doing this, the first thing to do is that we move the orthogonality center of the tensor network to the first qubit. So the orthogonality center is over here. So, and this means that somehow all of these other tensors, they are basically a unitary matrix. So if we now sum over this S2, I don't see why this is S4, this would be a S3, but anyway, so if we now don't ignore, let's say, all this extra S and we only focus on S1, so we can now contract all these indices together, and we can write the probability of detecting the outcome S1 as in terms of just this tensor over here and some contraction. So now we can write a classical probability distribution over just a single qubit variable, which is S1. And so we can sample efficiently using whatever sampling method like that you want from a classical probability distribution. And so now we get S1, which is our first sample. Now the idea is to define a Markov chain. So we want now to define the probability of getting the second S2, given that we have observed S1. And of course, you use the definition of the conditional probability. And now you can write the probability of S1 and S2 together, basically starting again from this structure, contracting everything except S1 and S2, and you end up into something like this, okay? And, but now, sorry, so now the trick is this one. So S1 here for us is given, because if you keep propagating this multiple times, so this becomes like very complicated. But now the main trick is that now S1 is known, is not a free index. So you can contract the S1 with the S1 that you have sampled at this stage over here. So the only free indices is basically S2. And you keep doing this. So you do this, and then what you do is that you combine together this tensor over here, you move it, and so you don't have to save all these tensors together, and you can repeat this idea multiple times to build like a Markov chain. So that's somehow the main idea behind the algorithm. So first of all, we tried to see what was happening using this model, and so we were simulating basically the von Neumann entropy, starting with, let's say, 20 qubits, and starting from different measurement angles. So you see that, for instance, when theta, so the measurement angle is close to pi/2, then the model is basically simulating a projective measurement. And so, I mean, after projective measurement, everything is like a pure state. And so there is no entanglement. If theta is equal to pi/3, then is a weak measurement. So it creates a moderate amount of entanglement, which stays constant in time. And on the other hand, if you keep increasing theta, then somehow this entanglement grows. And we can also do some scaling analysis to see how this entanglement behaves when you increase the number of qubits. And you see that clearly the red spot is always 0. For this weakly measured qubits, the entanglement remain constant in respective of the system size. And then there is a transition after a while. Somehow the entanglement entropy starts to grow and towards what would be somehow the volume law states. So here what we do here is that we repeat this measurement procedure multiple times, and we average basically over 1,000, well, we call them trajectories. It's basically repetition of this sampling experiment. So then we also started doing some scaling analysis to see whether somehow this Markov chain trick was somehow efficient. and we were doing all the simulations in basically in a workstation, so in a Xeon Gold processor using 32 threads, which is, I mean, okay, it's more than a desktop computer, but it's not anything near a supercomputer. It's still kind of a workstation. And everything was based on the iTensor library. And but of course, we had to heavily modify the library or adapt it to our needs in order to simulate, not modify the library, but somehow this is not a conventional algorithm that you can find in the library. So we were basically implementing this stuff using that library. And you can see that basically we were able to simulate circuits with small entanglement up to basically 500 qubits. And so the algorithm by itself is, I would say, is not a bottleneck. What is the bottleneck is clearly the bond dimension, because if you start increasing entanglement, that you need a larger bond dimension, which is what you see here in the yellow part with pi by 4. And for a larger bond dimension, everything becomes slower. And so even to simulate, I don't remember what number is this, I guess it's 50. Somehow you need the extra time. So just to give you an idea, so here every figure was, so even this 500 point was just a couple of hours in this processor. So I wouldn't say that's particularly time consuming. So, okay, so this is basically everything I wanted to say. So I'll jump to the conclusions. So we have an efficient tensor network-based algorithm, and by efficient, I mean ON, because you can show that somehow if you repeat this structure multiple times, then the complexity is just linear in the number of qubits. So we have this efficient ON tensor network-based algorithm to simulate the outcomes from these mid-circuit measurements. So the main trick is to apply this kind of Markov chain sampling. And the main computational bottleneck is not due to this extra algorithm, it's basically due to the usual tensor network machinery, which is efficient as long as the bond dimension is reasonably small. And so that's the bottleneck, not the Markov chain, I have to say. So for future applications, I would say this can be directly applied to measurement-based quantum phase transitions. But also my personal interest is to apply this to generative machine learning applications, mostly to write it in this language and basically study what I did show you in the first part of the talk for basically zero-dimensional problems in this more general structure. And another possibility to use this is for validating or calibrating quantum computers capable of mid-circuit measurements, because one of the advantages of this trick is that one can also simulate the measurement outcomes in a quantum computer. So if this is now a quantum computer, you can directly simulate with this algorithm the actual measurements as you would do in a quantum device, and so you can replace somehow this algorithm. So you can replace in a kind of library the simulation in the quantum hardware using this classical simulation, and basically use it as you were basically programming the quantum machine. And so you can use this in order to somehow validate the machine where the amount of entanglement is not too large, and so tensor networks are expected to be good. Yeah, so that's all. If you have any questions, yeah, please let me know. Thank you.
Well, keep Main question I have, because you mentioned mid-circuit measurement. So is the idea of like this, like approximate tensor network-based simulation to like simulate hybrid circuits? Is that the general idea of it?
General idea,
Am
what you
I So, for instance, you have a lot of like frameworks like Guppy, like Catalyst, like Qiskit. They're all moving towards mid-circuit measurements to enable classical control flow, right? And
yeah.
part of enabling classical control flow is being able to simulate classical control flow. So you can run it and you can show the users like what it means to have quantum circuits with classical control flow. And all of those usually just boil down to circuits with mid-circuit measurement, right? So
Mhm.
I'm wondering, you mentioned that you're able to simulate mid-circuit measurement, but also part of it, you mentioned that this is for weakly measured circuits. And I imagine there's a distinction between these, right? Between the measurement that I'm thinking of, I guess, which is like collapses to 0 or 1, and the weakly measurement that is mentioned here.
So the main idea for us was to not destroy entirely the system, just to partial. Well, I mean that's also the same thing here, the same thing for them. So I would say that so at least the last time I checked, I'm not sure whether Qiskit or these other libraries have the ability to do like tensor network simulations also for mid-circuit measurements. Is that what you're saying, or
No. So, because this is like a clarification from my part, in here, your mid-circuit measurement, does it collapse the state to 0 or 1, or no?
so this mid-circuit measurement does collapse the state to 0 to 1, but what we use is something more like this. So we have like so we simulate this mid-circuit as a weak measurement, but
Mm-hmm.
uh, so your question uh, is this limited to mid-circuit? Is this limited to weak measurements? I would say no, because the only structure that we care about is this one on the right. So the one on the
Because
right,
the,
so provided that somehow you have some qubits. So okay, so maybe another answer to your question is that somehow here what we have studied is that what you measure and what you don't measure, they are nearest neighbor. So that's what we studied here. I don't see any reasons to believe that you cannot extend this to more general settings where, I don't know, everything that you measure is on the left and what you don't measure is on the right. So the reasons why we did this is mostly because of the tensor network machinery. So because
mm,
measurements typically destroy entanglement, and so
yes.
if we make this measure, if we alternate measured qubit versus unmeasured ones, our idea is that in this way somehow you reduce the amount of entanglement between these blocks of two qubits, and so this could result in a more efficient tensor network simulation. So that's a trick. So that's like the only reason to alternate measured qubits and unmeasured qubits, or to write the weak measurements in this language. But other than that, I don't see why this. I I mean, I think this could be generalized to um, the other choices, I guess. I'm not sure if I answered
Because
your.
like I'm yeah.
Yeah,
So weak measurement, like as Dan mentioned, it seems to be a bit more towards quantum error correction, which I don't do at all. And most of my work is on the quantum compilation side. And mid-circuit measurement for me has been, very like simplified. Is that you measure a qubit, it collapses the state of your qubit, and then returns a binary bit, which is 0 or 1 to the user. And
yeah.
usually you take that and you do whatever you want with it. And the way that is simulated, at least because, and this is interesting for me because I'm actually reading this right now. And the way that it seems to be simulated these days is that every time you measure, because it's a non-unitary operation, you cannot do tensor contraction to represent it. You have to essentially branch your tensor into two individual tensors, and then from that point, if you want to update your circuit, you have to apply that tensor contraction to both of those. And each time you're measuring is essentially doubling the number of tensors you have to essentially,
Yeah.
propagate forward. So that one is very different. That
But
one's
that's
whole point is that.
yeah, but just to say that this is only because we wanted to simulate the weak measurements, okay? But in principle, you don't really have to double your Hilbert space. So for instance, if you are doing something like this, so where let's say you measure qubit 1, qubit 3, and qubit 5, so our algorithm can also be applied directly in this way. So you're not exactly grouping, so you're not doubling each tensor. So you start directly. So you never have this thing on the left. You start directly with this thing on the right. And so everything else basically follows because so the starting point of our approach is this thing on the right. So you contract what you don't measure, and then so this x1, x2. So this operation here is a projective measurement, so standard one. And so you keep doing this this kind of Markov chain, and everything is basically the same. So my point is that you don't need this. So just to directly apply our code, you need this structure over here.
Well, I'm sorry if I'm asking repetitive questions. So
Sorry?
I'm sorry if I'm asking repetitive questions or being a bit slow. Really, really sorry for that. I
Oh,
can
that's it.
actually wait until the end because I feel like I'm taking too much of the other people's time as well.
No, I don't know. I cannot see the chat. So where's the chat? Yeah, over
Yeah,
here.
I don't think we've got other questions in the chat, so I think you're good.
Okay. Okay. But anyway, so you can
I can ask.
oh, no, scan to interrupt.
Oh,
No,
thank you so much.
you can interrupt.
Yeah.
You can
So
interrupt. Yes. I don't know if there is
yes.
some other questions that I haven't answered.
I think that's about it as far as the questions that we have in the chat. Of course, you're welcome to continue chatting, but we are a little after time now, so I think we should probably wrap up in the interest of respecting everybody's time. But definitely feel free to continue the conversation on Discord or via email, anything like that.
All right. Thank you then. So if you have any questions, I'm happy to answer it by email.
All right.
Thank you.
Thanks, everyone.
Thank you, Leon.